All right, now that we have a way to name either our molecules that are covalently bound or our formula units that have ionic bonds, we can now think about describing how much do each of those different things weigh. So the same way that we talked about atoms having a specific mass that is determined by the relative amount of the different isotopes, we can, that had a defined mass. We can also say that molecules and formulas, or the formula unit that make up or that make up ionic compounds, they each both also have a very specific and defined mass. And we call that defined mass the molecular mass for molecules or the formula mass for our formula units. So this is the defined mass of a compound. And the way that we can determine that defined mass is we just sum all of the atomic masses. So sum of atomic masses. If a molecule is made up of different atoms, we could just sum the mass of each of those atoms. And so formulaically, you can take the number of atoms of your first element, multiply that by the atomic mass of that element, add to that the number of atoms in your the second element, multiply that by the atomic mass of the second element, and so on and so forth. And so let's look at a couple examples. Let's look at CO2. So we can look at the number of atoms of our first element is 1, and then we multiply that by the atomic mass of our first element. In this case, for carbon, that's 12.011 atomic mass units. So that's our first atom. Now let's worry about oxygen. We have 2 of those, and the weight of each of those atoms is the atomic weight of oxygen, which is 16.00 atomic mass units. So we can go ahead and multiply that through, and we get that the molecular mass for CO2 should be something like 44.01 atomic mass units. So this is the molecular mass. And we can look at this for formulas as well. So let's look at the formula unit for sodium oxide. We see that our first element here is sodium, and we have 2 of that. And the weight of each of those sodiums is going to be 22.99 atomic mass units. And we're going to add to that our single oxygen, and that single oxygen weighs 16.00 atomic mass units. We add that together, and we get that that's 61.98 atomic mass units. And then, as a final example, let's look at something that is composed of that has as part of it a polyatomic ion. So let's look at barium nitrate. So remembering that in this case, to get charge balance, we need more than one of our polyatomic, and we put that polyatomic in parentheses. And so now we can, go through. We have 3 different atoms, so we'll have 3 different additive terms here. We start with barium. We have a single barium. We look up in the periodic table, and we see that that barium weighs 137.3 atomic mass units. So this was our term for barium. So that was pretty straightforward, kind of follows through with what we've been doing before. Now we come to nitrogen. And so we see that we have nitrogen. As written, we have 1 nitrogen for every nitrate, but we have 2 nitrates that are part of this molecule. So we have this 1 comes from here, and then this is the 2. And then we multiply that by the atomic weight of nitrogen, which is 14.01 atomic mass units. So this is our term for nitrogen. And then finally, we have our term for oxygen, where each unit of nitrate has 3 oxygens, and we have 2 units of that nitrate. And then we're going to multiply all of that by our atomic mass of oxygen, which is 16.00, and this was all of our information for oxygen. And so in these cases, you don't have to show like this 1 and this 2. You could just say, I know in barium nitrate that there's 2 nitrogens and that there's 6 oxygens. Just the important thing to realize is that you want to distribute that subscript 2 to all of the elements that are part of your polyatomic, because that 2 applies to all of the elements within the parentheses. And so when you sum this all together, you get something like 261.3 atomic mass units. Okay? And so this is how we can determine the mass, or how much a given compound weighs. The last thing I want to talk about today is when we look at covalent compounds, so kind of flashing forward, or not flashing forward, but focusing just on one of our type of chemical bonds, there's a couple different ways we can represent that chemical compound. Where with the formula unit, we basically just have the lattice cell. With covalent compounds, we have two different ways we want to represent these. The first of these is the molecular formula, and that indicates elements present using atomic symbols. So elements present in a compound and actual number of atoms. And so, we indicate elements present in water as hydrogen and oxygen, and then we show the actual number of atoms by putting this subscript 2 here that says how many of that hydrogen we have. So this is our subscript number, and it tells how many of that atom. And we can also have things like H2O2 and even things like sugar. So C6H12O6. So we're stating the two elements present, hydrogen and oxygen, or carbon, hydrogen, and oxygen, and then the actual amounts by putting the number in subscripts. Being a little bit more exact and a little bit more descriptive, we have the structural formula. And what this does is it uses lines so lines or dots. So lines or dots to represent covalent bonds and show how atoms are linked together. How atoms are connected. Because when we just show things in the molecular formula, we don't know, is it hydrogen connected to oxygen, or is it, two hydrogens connected to the oxygen? We have to be a little bit more specific, and we do that using the structural formula. So we can have things like this that say that the oxygen is connected to each hydrogens, but the two hydrogens are not connected to each other. And you can also represent this with dots, where you put a set of two dots between each of the atoms that are covalently bound together. And you can also do the same thing for hydrogen peroxide, which looks like this. So you have H bound to the oxygen has a bond to the other oxygen that is then bound to the hydrogen. And then we can go from these structural formulas, like these are the two ways you'll typically see something depicted like in a problem, and we can actually expand on them a little bit more by giving some pictorial representations. And so here are, the representations for methane. So we talked about the molecular formula, which says type of element as well as the number. Then you can take that to the structural formula that shows the type of bonding present. And then you can actually show how that looks in 3D space. And so that's where this ball and stick and space filling model come in. They tell us how something looks in 3D space. So rather than, carbon in a plane connected to four hydrogens, there's actually some three-dimensional characteristic where things are spread out. So the ball and stick model gets a little bit more specific. So the molecular formula has the least specificity, then the structural formula, and then ball and stick. And then the final way that we can visualize a covalent compound is through the space filling model, which allows each of the atoms to take up, the amount of space it actually takes up relative to each other. And so we give carbon a large sphere, we give hydrogen's a small sphere, and you can see that now things have that overlap, and that overlap is because we took two atoms and we brought them together, and that's our chemical bond. And then also we can see that, with the space filling model, when things get large, you can see that they might butt up against each other. And so that's why things might separate from each other, why you might have hydrogens located as they are so that you can maximize the separation of them from each other. And you can do the same thing for more complex molecules like benzene, acetylene, glucose, and ammonia. Ammonia is basically one hydrogen short of our polyatomic ammonia. Glucose, is the sugar that we eat every day. And then these are a couple organic molecules. And so that's where I'll end the video for today. And we'll pick up from here in class on Wednesday.